Picture a single photon, the fastest thing there is, 300,000 kilometers a second, about 186,000 miles. Fire it against the spin of a rotating black hole just outside the edge and watch it stop. Not slow, stop, held in place by spinning space itself. The answer is a place called the ergosphere. The boundary where that happens has a name, the static limit. Cross it and no force in the universe can hold you still. Rockets at full burn, light itself straining backward, it makes no difference. Everything inside is dragged around the black hole in the direction it spins. Standing still stops being an option. Between that static limit and the event horizon, the true surface of no return, lies a shell of spacetime shaped like a flattened pumpkin. The Greek word for work is ergon. Two physicists, Remo Ruffini and John Archibald Wheeler, named this shell in 1971. The ergosphere, the place you can take energy out of a black hole. Go back to 1915. Albert Einstein publishes General Relativity. Gravity is not a force but the bending of space and time. Within months, on the Russian front of the First World War, an artillery officer named Karl Schwarzschild solves Einstein's equations for a single round star. His solution describes a black hole, but one that does not spin. And that was the problem. Nothing in the universe sits still. Stars rotate. When a massive star collapses, the same law that makes a spinning skater pull in her arms and speed up takes over. The core shrinks to a few kilometers across, and its spin winds up to hundreds of full turns every second. Real black holes spin. For 47 years, nobody could solve Einstein's equations for a spinning mass. Then, on the 1st of September 1963, a New Zealand mathematician named Roy Kerr published 2 pages in Physical Review Letters. Inside was the exact geometry of a rotating black hole. Physicists call it the most important exact solution in all of general relativity. Kerr's geometry held a shock. A spinning mass does not just curve space, it drags it. Like a spoon turning in honey, the black hole twists the very fabric of spacetime around with it, winding it tighter the closer you get. The effect has a name, frame dragging, and near a black hole it becomes overwhelming. The idea was not new. In 1918, 2 Austrian physicists, Joseph Lenz and Hans Thüring, worked it out from Einstein's equations. Any rotating mass should drag space around it just a little, even the Earth. The effect was so tiny that for almost a century, nobody could measure it. It stayed a line in mathematics. Then NASA built a machine to feel it. Gravity Probe B carried 4 quartz spheres, polished so smooth that if each were the size of the Earth, the tallest mountain would be 3 meters high, about 10 feet. On the 4th of May 2011, the team announced the result. Earth drags spacetime around itself, exactly as predicted. If Earth's gentle spin can twist spacetime by a measurable thread, picture the same effect around an object that has folded the mass of a star into a sphere a few kilometers wide, turning hundreds of times a second. Frame dragging stops being a whisper. It becomes a current no rocket can swim against. That current carves out the ergosphere. The static limit is not a sphere. It bulges at the black hole's equator and pinches in to touch the event horizon at the poles, that flattened pumpkin shape. At the equator it reaches farthest out, because that is where the spin drags hardest. Picture a whirlpool. The pull is strongest at the rim, weakest along the axis. Step inside the static limit and the rules change. You can still escape. The true point of no return is deeper in, but you can no longer hold position. To an astronomer watching from far away, everything in the ergosphere is sweeping around the black hole, dragged by space. Even a beam of light aimed against the spin is carried forward. So why the sphere of work? Because in 1969, the British mathematician Roger Penrose realized something extraordinary about this dragged-around shell. You could go in and come out richer. You could reach into a black hole and pull energy back out. He published it in the journal Rivista del Nuovo Cemento. It is now called the Penrose process. Here is his thought experiment. Send an object into the ergosphere. At the deepest point of its dive, split it in two. Fire one half inward toward the black hole and let the other fly back out. Choose the angle carefully, against the spin, and something impossible happens. The half that escapes comes out carrying more energy than the hole had going in. The trick lives in the ergosphere alone. Inside that shell, because space itself is being dragged, certain orbits carry what the mathematics calls negative energy, less than nothing, measured from far away. Feed the inward half onto one of those paths, and it subtracts energy from the black hole as it falls. That stolen energy is handed to the half flying free. Nothing is created from nothing. The energy is real and it is paid for. Every time the Penrose process runs, the black hole spins a fraction slower. You are not breaking the laws of physics. You are draining the black hole's rotation, converting its spin into usable energy and carrying it away. A spinning black hole is a flywheel the size of a star. How much is in the tank? In 1970, a young Greek physicist, Demetrios Christodoulou, working with Penrose's geometry, found the limit. For a black hole spinning as fast as nature allows, up to 29% of its entire mass could be drawn out as energy. Not 29% of its fuel, 29% of everything it is. Hold that against the engines we know. The fusion that powers the sun converts 0.7% of its fuel into energy. The reactors that run our cities, far less. A spinning black hole offers 29%, the most efficient source the laws of physics permit, short of matter meeting antimatter. The best engine in the universe is a hole in the sky. Christodoulou found something deeper, too. As you drain a black hole's spin, the area of its event horizon never shrinks. He called the part you can never remove the irreducible mass. That one rule, the horizon's area can only grow, became, through Stephen Hawking's later theorem, the foundation of black hole thermodynamics. Penrose did not leave it as abstract mathematics. In his original paper, he sketched who might use it. An advanced civilization orbiting a black hole that has run out of other power. They would lower a weight on a cable into the ergosphere, release a load on the negative energy path, and haul the rest back up, heavier with stolen spin. Picture the scale. A shell of habitats wrapped around a black hole, the way Freeman Dyson once imagined a sphere built around a star. But this engine never runs out of fuel. It feeds on rotation, and you can top up the rotation by throwing your rubbish in on the right path. Rubbish in. Power out for as long as the hole spins. The process has a wave-shaped cousin. In 1971, the Soviet physicist Yakov Zeldovich asked what happens when you shine a wave at a spinning object instead of throwing a stone. He found a rotating, absorbing body could send the wave back amplified, stronger than it arrived. The body pays by slowing down. The effect is called superradiance. Around a spinning black hole, superradiance turns the ergosphere into an amplifier. A wave of light or gravity sent in against the spin comes back stronger, having skimmed energy off the rotation. Wrap a mirror around it and the wave bounces, amplifies, bounces, amplifies. A runaway engine the theorists call a black hole bomb. On paper, at least. Then nature showed us it had been doing this all along. In 1977, Roger Blandford and Roman Zinajic worked out the version that uses magnetism. Thread a spinning black hole with a magnetic field, and the dragged spacetime of the ergosphere winds those field lines like a dynamo, flinging energy outward along the axis. Just spin, and a magnetic field. This, we now think, is how the brightest objects in the universe shine. Quasars, the cores of galaxies that outshine every star around them combined, are powered by giant black holes feeding and spinning. The Blandford-Zinajic process taps their rotation and fires it back into space as beams of plasma traveling near the speed of light. You can see one. The galaxy Messier 87, 55 million light-years away, holds a black hole of 6.5 billion suns. On the 10th of April 2019, the Event Horizon Telescope gave us its first photograph, a ring of fire around a shadow. And streaming from that core is a jet of plasma 5,000 light-years long. Closer to home, in the constellation Aquila, a black hole called GRS 1915 drinks gas from a companion star. By reading the X-rays from its inner disk, astronomers measure how fast it turns. It spins at something like 98% of the absolute maximum Roy Kerr's equations allow. Its ergosphere is real, vast, and turning almost as hard as space-time permits. How do you weigh the spin of something you cannot see? You watch the light from the gas falling in. Iron atoms in the inner disk give off X-rays at a sharp, known energy. The black hole's gravity and frame dragging smear that line, stretch it, drag its edge. The shape of the smear tells you the spin. At the center of our own Milky Way sits Sagittarius A star, 4 million times the mass of the Sun, 27,000 light-years from where you are sitting. The Event Horizon Telescope photographed it on the 12th of May 2022. It almost certainly spins, which means our galaxy is built around an ergosphere at its very heart. This is the part worth holding on to. The ergosphere is not a thought experiment anymore. It is not science fiction. It is a region of spacetime we have mapped, photographed the edge of, and measured the spin of around real black holes with real names and real positions on the sky. The map has labels. The labels point at engines. What would you see falling toward one? Behind the black hole, the whole sky bent into a ring, light from stars dragged around and around before reaching your eye. The static limit would not glow or hum. There is no wall, no membrane. You would simply notice you could no longer stop moving sideways. Space had taken the wheel. And here is the mercy of the ergosphere. It is survivable in principle. The static limit is not the event horizon. You can dip into the dragged region, lose the ability to stand still, and still climb back out, as long as you do not cross the deeper line. That is the whole basis of the Penrose process. Go in, take energy, come back. Time, too, behaves strangely in the shell. The same frame dragging that sweeps you around also tilts the direction the future points. Clocks, light, causality itself are wound around the spin axis. The mathematics that describes it, Roy Kerr's metric, remains one of the strangest and most studied objects in physics, 6 decades on. Engineering numbers and the fantasy turned sober. A civilization harvesting a spinning black hole could, in theory, power itself for longer than the current age of the universe, on the rotation of a single dead star. No other source we know comes close. The catch is everything else. The tides, the distance, the centuries of construction. Near a stellar black hole, the difference in gravity between your head and your feet would pull you into a thread. Physicists call it spaghettification, and they are not joking. A supermassive black hole is gentler at the edge, but reaching one means crossing tens of thousands of light years. The ergosphere is the most generous power station imaginable, in the most hostile place conceivable. Still, the principle stands, and the universe runs on it. Every quasar that has ever blazed, every jet of plasma punched thousands of light years out of a galaxy's heart, is the Penrose process and the Blandford-Zenagic process at industrial scale. Black holes are not just where things end. They are the most powerful engines that exist. And the bookkeeping that began here, Penrose in 1969, Christodoulou in 1970, grew into something larger. The rule that a horizon's area never shrinks led Jacob Bekenstein and Stephen Hawking to give black holes a temperature and an entropy. The ergosphere, where we first learned to take energy out, helped teach us that black holes obey the laws of heat. Roger Penrose, the man who first saw how to reach inside a spinning black hole, received the Nobel Prize in Physics in 2020. Not for the energy process, but for proving that black holes are a genuine prediction of general relativity, not a mathematical accident. The ergosphere was one of the strange, true things geometry insisted had to exist. So somewhere out there, right now, a shell of spacetime is turning. Around Sagittarius A star at the center of our galaxy. Around the 6 billion sun engine in Messier 87. Around GRS 1915, spinning at 98% of the limit. Each one a region where standing still is forbidden, and where the rotation of a dead star waits, like charge in a battery. We have photographed the edge of it. We have measured how fast it turns. We have the equations 60 years old that say how much energy is locked inside. What we have never done is reach in and take it. Maybe no one ever will, but the physics does not forbid it, and the universe is not obliged to make sense to us. The ergosphere is out there, spinning full.